Okay, in the previous video, we talked about how to find the tangent slope by using a concrete example, y equals x squared. We took points that were close to the point 2,4 and kept moving 1 point closer and closer and closer. So basically using secant slopes to kind of figure out that what does that secant slope look like it's approaching, and that's what we think the tangent slope is. Well, now we're going to use generic points so that we can get an actual concrete formula for this. So what we're going to do is I'm actually going to cheat a little bit. At least I'm going to try to cheat a little bit here. Let's try this and see if it works. Nice. Got these little tools I'm just not used to using. Anyway, the only difference here is that this line technically should go on forever in both directions. So I'm going to go ahead and add the arrow down there at the end instead of a point. Okay, so here's a line that's going to represent a secant line through some kind of a curve. So let me go ahead and draw the curve. So the curve, I'm going to actually draw that in black as well. Curve might look something like this, something like that, and that's the part of the curve that we're interested in. We're going to call this point right here point P. So that's point P. And then we're going to call the point up here point Q. So now if I wanted to find the actual slope of the tangent line at the point P, the idea is what I would do is I would take that Q point and I would move it along this curve right here. I would move it along here until it gets so infinitely close to P that you really can't tell the difference. But for right now, what we have here is the slope between P and Q. So let's go ahead and see what that looks like. Well, we have to define the point P. Okay, it's got some kind of an X value and some kind of a Y value, so does Q. And yes, I understand that what I'm getting ready to show you doesn't make a lot of sense. You're like, well, why don't you just use X? We're going to call this specific value C. Okay, that's just what we're going to call it. It could be any constant, which is why they call it C, along the number line. So that means that the actual ordered pair for the point P is the point C, comma, and then the Y value. Well, if you want to find out the Y value given an X value, you plug it into the function. So considering that this is some kind of a function, we're going to call the second value here f of C, the function evaluated at C. Remember, f of x is just like saying y, so f of C is just the y value. So C comma f of C is your x and your y value for that ordered pair. Likewise, we're going to have one over here for Q. Make that one a little bit bigger because I know what's coming there. To get from the point C to the next point X over here on the second blue dash, well, there's some kind of a change. Excuse me, there's some kind of a change of X. So the distance between here and here is a change of X. And we use this little triangle to represent the word change. That means the change of X. Very common mathematical and physics notation. Change of X. So that means that this point over here is going to be C plus our change of X. That's the X value right there. So that's my X value in my ordered pair, C plus a change of X. Well, then that just makes the Y value, just like before, it's the function evaluated at that. I'm actually going to have to erase this. Didn't give myself enough room there. That'll be the function of C plus delta X. So now that's the hard part. That's the setup. Hopefully you can see how all that stuff fits together. Now if I want to find the slope of the secant line, it's y2 minus y1. Well, y2 is f of C plus delta X. So f of C plus delta X minus y1, which is f of C, over x2, which is C plus delta X, minus x1, which is c. Now, the top piece cannot really be simplified at all. Those are two functions evaluated at different things. So it's just going to give me the function evaluated at c plus delta x minus the function evaluated at c. But the denominator can. I've got c plus delta x minus c. Well, the c minus c goes away. That's 0. So it just leaves me with delta x. That right there is the slope of the secant line. And you might recognize this. We did stuff like this in prior math classes. This is what is called the difference quotient. It probably looked a little bit different. It probably looked like f of x plus h minus f of x over h, or something to that effect. Anyway, that's called the difference quotient. That is exactly what we have here. This difference quotient is just a slope. That's all that it's giving you. It's the slope of the secant lines. And again, the idea was if we take Q and we move it infinitely close to P, then what we're really saying is the slope of the tangent line, so the slope of the tangent line is the limit of these secant slopes right there. It's the limit of that. So we'll actually have to write the word limit out in front of it. We're going to get to all that in a different section in much more detail, but that's the general idea. All right, so now let's go ahead and look at what's called the rule of 4. I love that I call it this because I can only ever remember 3. There's algebraic, graphical, numerical, and I think the last one might be analytical, but I don't really use that one very often. So we're going to call it the rule of 3, maybe 4. Anyway, so what we have done is we have looked at a graphical idea of a limit, and we have looked at, and we're going to look at a numerical and algebraic idea of a limit. So let's kind of just go back to our idea of a parabola. And here's what we want to look at. Let's say that we have this parabola, but right there on the parabola, there's actually a hole. Now, granted, a hole is a very, very small thing, but we have to kind of over-exaggerate those on a graph so that we can actually see it. So let's say that that's 2. Now, you might be saying, how do I know that? Well, let's go up to our function. The function is x cubed minus 2x squared over 3x minus 6. And you might be thinking, that's not a parabola. You're right, it's not a parabola because it has a hole in it, so it's technically not a parabola. But what we can do is we can simplify this. Okay, we can factor on the top. We can factor an x squared out of the top, which leaves us with an x minus 2. And then we can factor a 3 on the bottom, which also leaves us with an x minus 2. And if you were to plug 2 into the top and the bottom, it gives you 0 on both the top and the bottom, which gives you a hole in the graph. And then while we're technically not going to do it, if you were to cancel out those x minus 2's, you would have x squared over 3 left over, which is basically just a parabola. It's 1/3 x squared really is what that is. So this is a parabola, but there's a hole at 2, because if you plug 2 in, you get a hole. So the idea is, what's the limit as x approaches 2? That's what we're looking for. So we really want to find out, as my x values come along this curve right here and get closer and closer and closer to 2, what is the actual limit? Or is there a limit? And the answer to that question is going to be yes, there is a limit. And the easiest way to define that is, what does the y value approach? The y value doesn't actually have to be there, but what would that y value right there be? That would be our limit. Remember, you don't actually have to be able to attain the limit. It's what do you actually approach? What is it getting close to? That's really the idea of the limit. So we can do it numerically. Now, this you would require your calculator for. You would have to, in this chart on the right side, you'd have to plug these values into your calculator. This is definitely not something that would be anticipated you would do in your head, because you'd have to plug 1.97 into f of x and see what you get. Fortunately, I've worked all that stuff out for us already. So if we were to plug in 1.97, you would get 1.2936. And it may go on even further. I don't remember. I just stopped after 4 decimals. If I were to plug in 1.98, you might say, why am I plugging in 1.98? Well, that's getting closer and closer to 2. So if I plug in 1.98, I get 1.3068. 1.3068. And you might want to try some of these on your own just to make sure you're able to plug this stuff in the calculator. You plug in 1.99, you get 1.3200. 1.3200. If you were to plug in 2, we've already said that that's going to be a problem. If you actually plug in 2 in your calculator, it's going to tell you like error or something like that, or undefined. I don't know if it actually says undefined. I think it says error in the calculator. And then if we approach it from the other direction, from the higher side, from numbers above 2, if I plug in 2.03, now I'm skipping to the bottom one here, that's 1.3736, I think, 1.3736. And then if I plug in 2.02, it's 1.3601. And then if I plug in 2.01, it's 1.3467. Now what you should be able to do is kind of see, as the numbers get closer and closer to 2, what do the y values or the f of x values look like they're approaching? Well, the ones from the lower side, it's got 1.32. The ones from the upper side look like it's like 1.34. So a logical guess might be 1.33. And in fact, 1.33 repeating is the same thing as 4/3 as a fraction. So we'll actually do the algebra part of that later. But it looks like, or it appears as if that y value where the blue L is would be about 1.33 repeating, or 4/3. So what we would say is the limit as x approaches c, in this case our c value is 2, the limit as x approaches our c value approaches or is our limit. This is the notation that we'll use, where L is just whatever the limit is, f of x is the original function, and c is the number that we're approaching. So let's kind of look at that below. This is the c part, this is f of x, and the limit right here we think is 4/3. At least that's what it looks like it's approaching. So hopefully you can see numerically the idea. You want to basically find values that start to get closer and closer and closer to your number, and then see what it approaches from both sides. Very, very important on this last one, which is why it says important. I am going to star this. Oop, didn't really want to do it in that purplish dotted thing. Let's do it in red instead. Let's star this. This is a very, very important concept. It says the existence or the non-existence of f of x at x equals c has no bearing on the existence of the limit of f of x as x approached c. Okay, what does that mean? In this case, there was a non-existence of a value. F of x did not exist there, but that had no bearing on whether the limit existed in this case. The limit still exists. The limit looks like it's approaching 4/3. So whether that point in there was a hole or whether it was filled in and it actually was a point would make no difference. As x approaches 2, looks like the limit or the y value is approaching 4/3, even if it's not actually there. It's what does the limit approach. So the existence or the non-existence of f of x or the y value doesn't matter in this case. Very important concept. All right, now let's talk about an actual problem. One of the most common ones that we talk about here is the velocity problem. So first question is velocity constant? Well, in real life, not generally. And we'll say it that way because for a very small amount of time, you could probably find a constant velocity of things, but not generally. I mean, if you think about think about driving a car. And for those of you guys who are too young, think about riding in the car. you drive a car, if you're riding in a car and you're driving along the road, it's very, 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 very extremely seldom that you can maintain a constant velocity the entire time that you're driving. Even if you set cruise control, while it does its best to maintain that speed for as much as it can, it's going to fluctuate up and down. You know, you set your cruise control for 60 miles per hour, it's going to slow down below 60, it's going to speed up depending on traffic, depending on the roads, the incline, all that kind of stuff. So how do we define instantaneous velocity? Well, the instantaneous velocity of something is the velocity at one specific moment in time. So it is velocity at one moment in time. So basically the idea is you're driving down the road, you look down at your speedometer at a very specific time, it says 58 miles per hour. At that one specific moment in time, that was your instantaneous velocity. The velocity at one instant, at one moment in time. So we're going to take a look at an example here from a textbook, and it's actually from the textbook that we use, or at least it used to be. I don't know if it's still in there anymore. Here's the idea. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, which is 450 meters above the ground. So we're just going to take a ball and drop it off this deck. Very high. Find the velocity of the ball after 5 seconds. So obviously this ball is going to start to drop. We want to know what its velocity heading towards the ground is at exactly 5 seconds. Okay, not easy to do. But what we can do is, since we know the basic formula for that, S in this case represents distance. I don't know why. Not sure why the S is there. I'm sure it has something to do with its origins in a different language or something. But S represents the distance fallen after t seconds. So t is time, S is distance. Well, average velocity is the distance that you travel over the time elapsed. So how far did you go over how long did it take you to get there? That's distance traveled. Whoops. There we go. If we want to find the distance, now this is kind of important notation, between the 5th and the 6th second, that's this one, between 5 and 6 seconds. You might also see this, by the way, written like this. 5, 6, solid brackets on each one. That's called interval notation right there. That would just mean between the 5th and 6th second. Well, it's just going to be a y2 minus y1 over x2 minus x1, where basically the t values are x values. And so to find the y values are going to be done by placing those two x values into the function. So if I want to find the average velocity between the 5th and the 6th second, I need to figure out what the position is at the 6th second. So S of 6, I have to subtract the position at time 5, S of 5, over the difference in time, which is 6 minus 5. So if we plug these in the calculator, I'm not going to write every piece out here, but you would do 4.9 times 6 squared minus 4.9 times 5 squared, and then you would do over 6 minus 5, which is 1, of course. You would get 53.9 meters per second. Okay, that's an average velocity over that 1 second time interval. But I'm not looking for the average velocity. I want to find the instantaneous velocity at 5 seconds. So what can I do? I can take that time interval and I can shorten it. I can say, okay, 1 second is too big. Let's see what the difference in the time is. Difference in the distance over the time is if I let the second time be 5.1. So now I'm only talking about 0.1 seconds difference. So now we need to do S of 5.1 minus S of 5 over 5.1 minus 5. And again, you're going to plug in 5.1 and 5 into your function, get those values, subtract them. over top of 5.1 minus 5, which is 0.1. So you're going to end up with 49.49 meters per second. Okay, so you can see that the average velocity changed. It actually went down over that time interval. Probably don't have enough information yet to actually come up with an actual instantaneous velocity. Like, it's hard to tell what this is approaching because there's a difference of almost about 4.5 or so meters per second. So let's get a little closer. Instead of 5.1, now let's go 5.05. So 0.05 is closer to 5 than the 0.1 was. So again, it's going to be S of, this will be the last time I write this part, S of 5.05 minus S of 5 over 5.05 minus 5. And then we're going to go ahead and plug that in the calculator, and you get 49.245. 49.245. So now you might be able to hypothesize what you think this thing is approaching. And as a matter of fact, I'm not going to write the other ones out completely. I'll just give you what the answers were. If you let the distance become even shorter to 0.01, it becomes 49.049 meters per second. And then if we add another 0 in there and make it 5.001, it becomes 49.0049. And obviously, the more zeros you add in there, the more zeros you're going to have in your answer. And it certainly does appear that this velocity is approaching, as we let the time intervals get really, really, really close together towards 5, it appears like we're approaching 49 meters per second. And so we're going to say that that's our hypothesis here, that this is 49 meters per second, because that's what the limit of those secant slopes, which is exactly what we've been doing, the limit of those secant slopes is approaching. So the instantaneous velocity is defined to be the limiting value of the average velocities. So the average velocity, average slope. Instantaneous velocity, tangent slope. Same idea. And we're going to do those over smaller time periods. Okay, I hope that makes sense. Let's do one more and then we'll finish this video off. So like I just said, the slope of the secant line is the average velocity. If you think about that, that makes sense. 2 points is going to give you an average. The slope of the tangent line, which hits at only one specific point, is your instantaneous velocity. All right, one more example. I'm going to roll through this one a little bit quicker because all it is the same idea. I'm actually just going to kind of give you the numbers as we go after the first part, and then we'll be done with this lesson. So our last example is the displacement in feet of a certain particle moving along a straight line is given by s equals t cubed over 6, where t is measured in seconds, and again, s is your distance. So we want to find the average velocity over the following time periods, and here are those bracket notations that I told you. So the first one is from times 1 to 3. So that means I need to do s of, I need to do s of 3 minus s of 1 over 3 minus 1. And s of 3 here is actually 27/6. S of 1 is 1/6 over 2, which is going to be, what is that, 26/6 over 2, which, let's see, if you do a little bit of reduction there, that's going to give you 13 over 6. Remember, you bring the denominator, which is 2, up, flip it over, and multiply it. And that is going to be approximately, as a decimal, 2.167. And what are we in here? Feet in seconds, so feet per second. Units will become very, very important in this class, so make sure you're good with the units. Traveling at 2.167 feet per second. Okay, if we go between 1 and 2, again, you're going to plug in 2, so s of 2 minus s of 1 over 2 minus 1. Again, I'm not writing all that out. You're going to get 1.167 feet per second. And then if we make the distance between time 1 and the second time closer, maybe 1 to 1.5, you're going to get 0.7917 feet per second. Kind of tough to see what we're approaching. We went from about 2.2 seconds to 1.2 seconds, so that's about a 1 difference, down to 0.79. So, you know, we're looking at maybe about 0.4 difference now or so. Kind of tough to see what we're approaching. So we need to get closer and closer so we can see what the pattern is. So we'll do 1 to 1.1. Again, plugging in the 1.1 and the 1 to find your y values, you get 0.5516 feet per second. Still kind of tough to tell because now it's a difference of about 2.4 or so. I'm sorry, 0.24, excuse me. So we're probably going to have to add some letters in here, as a matter of fact. So let's add an E, which was going to be from like 1 to, I don't know, 1.00000, has that 4 zeros, 1 maybe. That's pretty close, right? I mean, those two values should be really close to each other. So that ought to give us a really good approximation, I would think, here. So if we plug those values in, you're going to get you're going to get 0.500001. I think you pretty much have a good idea what that's approaching at this point, feet per second. It looks like the instantaneous velocity when t is going to 1 is going to be about 5 feet per second. Sorry, 0.5. I keep saying 5. 0.5 feet per second. All right, that is plenty long enough. I apologize for the length of the video, but that should be plenty enough for you guys to do what you need to do.